All right, I've got 6 formulas up there, but technically only 3. The best thing for you is to remember which ones the negative ones are. Now, you've seen some inverse trig before. What I want to remind you in Calc would be sine inverse would be the same as arc sine. So in Calc, a lot of times the old notation's used, the arc sitting there. I don't know if many of you saw that last year or not, something like that. So even like tan inverse, arc tan. We see both, all right? So we just kind of get used to it. All right? So I wrote the formulas with the inverse notation for the derivatives. And we're only going to look at the derivatives today. Next time we'll look at the integrals. And on the integrals, you only need these 3. Okay? So if you can work on memorizing the derivative pieces, then you're set for the integral pieces. And then memorizing which ones go with which. So when I say the derivative of the cosine inverse is the negative of the sine inverse, this means there's a negative there. That's it. So the cotangent inverse is this one negative. The cosecant inverse, this one negative. So if we can tie them together, remember which one's which, it'll help us. All right, and we'll look when we do the integration why we don't need these 3. It's going to show up. If we can get these 3 down, we're pretty good. Something like that. Now, as far as the derivative pieces, remember when you're taking a derivative, the chain rule still applies. Chain rule still applies. So if you look in your book, they'll write the derivative like this. Where they've already kind of substituted a u in. It just doesn't look correct because you've got an x here and a u here. Those variables should match. Okay? But they're doing it to show you, hey, don't forget about this u prime up here. Okay? Well, what we've talked about all along with derivatives is there's always a chain rule involved. So I'm expecting you to remember that. So the derivative of this is this times the derivative of the inside, which the derivative of x is 1. So if that was a 2x there, you'd have a 2 out here. Everybody okay with that? We're already used to doing that. So that's why I don't write it like this. I kind of keep it with the x's. So you're used to it. Just remember we're always applying that chain rule. So let's say I want the derivative. We'll do a sine one first here. Sine inverse of 3x. Now the toughest thing to get used to is just knowing the different rules. So just keep them close. Right? So looking back at them so you can work on the patterns. The actual filling stuff in and doing the chain rule, that should be pretty simple to you. There's not much going on there. So we would have 1 over square root 1 minus 3x squared. So your rule is whatever's here. This was just an x. Okay, so now it's a 3x. It's going to be 3x squared times the derivative of the inside, 3. Clean it up a little bit. I mean, this is correct. I'm going to put a 3 on top. Square root 1 minus 9x squared on the bottom. You okay with that? The worst part is the simple fact that you have 6 or 3 new rules. That's the worst part of it. So if I said the derivative with respect to x of the cotangent inverse of 7x. All right, cotangent's not one of my 3 main ones, so then I'm thinking of which one is the negative of. Cotangent's the negative of the tangent one. So all it's going to do is put a negative right here on the top. So we would have negative 1 over 1 plus 7x squared, and then times 7 for that chain rule piece. Everybody okay there? Clean it up a little bit. Negative 7 over 1 plus 49x squared. Everybody okay there? Okay, now let's mix in a few things that we've done. Let's go with, done recently anyway, derivative with respect to x. And let's go arc secant of e to the 2x. All right, so the first thing, here comes that arc notation. We want to remember that arc secant is the same as secant inverse. All right, it's just the old form notation versus the newer inverse looking form. Nothing wrong with that. Here comes this e. We've seen e here recently. We've done the derivative of e, all that kind of stuff. So nothing new on that part. So let's get it put in. Be 1 over absolute value e to the 2x times the square root e to the 2x squared minus 1. So again, whatever was on that inside. And then now the chain rule. E to the 2x times 2. Do like you've done in the past. Take the time, write out the raw form. You have everything written out. If you have a mistake or you think you've got a mistake, you can look back at your raw form and kind of figure that piece out. Right? And then worry about getting this simplified form. So now my simplified form. You actually cancel e to the 2x out with e to the 2x. In this case, 2 would go on top, 2 over e to the 4x minus 1, and that inside that square root.
So would you always be able to cancel, or is it just because the absolute value doesn't matter because it's an even power right now?
There you go. It's not going to matter because that even power is going to stay that positive. I'm not worried about that piece. All right, let's get a couple other things that we've seen before. Let's go with derivative with respect to x of x cubed arc cosine of e to the x All right. What's the overlying rule we'd use here? Product rule. If we read it, we read x cubed times an arc cosine. So all those other rules are all still at play. There's nothing wrong with it. So my product rule. First, x cubed. Derivative of the second. So there's my new one, arc cosine e to the x. Would be -1 over square root. So we're saying it's the negative of the sine inverse. 1 minus e to the x squared times the chain rule, e to the x. Plus the second, arc cosine e to the x times the derivative of the first, 3x squared. Now it looks, a lot of times when you're first looking at it, especially one like this where you went through a product rule, looks horrible because it's just strung out, a lot of things going on. But focus on what we did. We stuck right to our product rule. First, derivative of the second was the only new piece here. Okay? Plus second, derivative of the first. The product rule has not changed. If we go to simplify, not a whole lot I can do. I can do negative x cubed e to the x up top, square root 1 minus e to the 2x. And then usually we'll see those smaller ones like the 3x squared come into the front. Does not matter though. And there's not much else we can do. I guess we could factor out x squared from the top, or we can get a common denominator, but it's not going to make it look any better in this case. Everybody okay there? All right, you write out the long form of this one. Derivative with respect to x. Let's go 2 to the 4x sine inverse 1 minus x. So still a product rule. Using two new rules this unit. That 2 to the x or that a to the x. And now it's sine inverse. So just write out the long form, then we'll kind of check that piece. Yeah, it's a 4x up there. 2 to the 4x. All right, what do you think there? Look okay to everyone? And notice I just went right through the products rule. I didn't try to combine anything. I'll go back and do that. Okay? I'm working right through my rule, especially when I've got a couple new things going on here that I'm not necessarily as familiar with. As far as combining, there's not really a whole lot that can be done. I'm going to put this 2 and this negative 1 up at the top. Okay, so I can make that negative 2 to the 4x over. A lot of times in the simplified process, we'll see this multiplied out. So if I did 1 minus x squared, so inside there it's 1 minus x squared like that. 1 minus, then that would be 1 minus 2x plus x squared. So then that would be 2x minus x squared. Those are the ones we cancel. So square root 2x minus x squared. And then there's not much we can do here. Typically, we'll pull the numbers in the front, but it really doesn't matter. There's nothing we can really combine over on this part. So I have plus 4 ln 2 times 2 to the 4x sine inverse 1 minus x. We could even move the 4 up and make it 2 to the 4th, which is 16, our log properties. But usually this is the one that gets people. All of a sudden we're here. Well, where in the world did this come from? We've got some binomial square. Take the time, multiply it out, then you can combine like terms. It's just not as easy to go from right here to here, or sometimes not even from right here to here, without writing it out. So if we can get this raw form, that's the key. Any of our new rules we've seen since the beginning for all these derivatives, we write our raw form out first, simplify where we can. Focus on that part. How about this? Let's go to the derivative with respect to x of the tangent of the arc cosine of x. Write what you think. All right, the outlying function's the tangent, right? What's the derivative of tangent? Secant squared. So we're going to have secant squared of the arc cosine of x. So derivative of tangent, secant squared of this, times the derivative of the inside. So this is my chain rule piece, arc cosine x. Should be -1 over the square root 1 minus x squared times 1. No, I don't need that 1. I'm just reminding myself there's a chain rule on that x. Right, okay there? It looks like a complete mess, but the 1 on the outside is not going to matter. I can also change the form. Do you remember from Trig how to evaluate something like this? If I wanted the tangent of the arc cosine of something. Do I remember what you did to figure that out? Draw the triangle. What's that x really over? What's the x over right here? X over what? 1. So you really have two numbers, right? Which means you really have two sides of the triangle. You have the adjacent, and you have the hypotenuse. And that's SOHCAHTOA. I just call it theta. Here's adjacent, here's hypotenuse. So wouldn't this be the square root of 1 minus x squared?
Yeah.
Pythagorean theorem. Everybody agree with that? So now what's the tangent of this? Opposite over adjacent. Everybody agree with that? Everybody okay there? Now, get rid of this guy. Let's find the derivative with respect to x of that. What rule do you use? Quotient. Okay. So, bottom, through the top. -1/2 negative 2x. Bottom, derivative of the top, 1/2 comes down. 1 minus x squared, negative 1/2. That's negative 2x minus the top. Derivative of the bottom's 1 over the bottom squared. Simplify a little bit. Let's see, the 2's are cancel. So I'd have negative x squared over the square root 1 minus x squared minus the square root 1 minus x squared all over x squared. Not much I can do to these two pieces, but here the 2's cancel. X times x is x squared. Drop that to the bottom. Look okay? I can clean this up a little bit. I can multiply everything by this denominator right here. So it would cancel here, be right here, and then be on the bottom. So I'd have negative x squared minus 1 minus x squared over x squared square root 1 minus x squared. X squares cancel. So negative 1 over x squared square root 1 minus x squared. Are they okay there? Those two answers are the same. One just has a trig function sitting in there. You can see the negative 1 over the square root right here. That 1's not going to matter, right? It'll be gone. So let's investigate the first part. Again, you're drawing the triangle. x1. So if the cosine's x, that means the secant's 1 over x. So this piece right here is 1 over x squared times negative 1 over the square root 1 minus x squared which is negative 1 over x squared square root 1 minus x squared. When you get trig functions, one trig function of another, you can get it back into an algebraic format like you did with trig, take the derivative. Or you can work with the trig function. This is correct. This is absolutely correct. This, a lot of times, is what you're going to see. All right, so it's still going to go back to drawing that triangle to kind of figure out the pieces. Everyone okay there? Do you remember drawing the triangle out? And we'll give you another example, just drawing the triangle. Let's say I had sine inverse of, I don't know, I'll put 2x. And I have just whatever out here. I don't care what trig function is out there. It does not matter. It doesn't affect how I'm drawing the triangle. Matter of fact, the only thing that would make it easy if there was a sine out there, because then it would cancel out the sine inverse. But the triangle's drawn off the 2x. And that's 2x over 1. And this is a sine function, opposite over hypotenuse. Still right out of that SOHCAHTOA. Pythagorean theorem, square root 1 minus 4x squared. If I square 2x, I get 4x squared. Now, whatever was out here, you can operate. If this said tangent, 2x over this. If it said cosine, this root over 1. If it said secant, 1 over the root. If it said cotangent, the root over 2x. This isn't your issue. The triangle's drawn off that inside. The outside part should be pretty easy to us because now we have all three sides of the triangle. It doesn't matter what trig function we're asked for. We're right back to doing that SOHCAHTOA. If I need cosecant, secant, or cotangent, I'll find the original and flip it over. Something like that. If I actually put a fraction in here versus let's do like an x over 5 versus a 1 down there, get something like that. It's still opposite over hypotenuse, x 5. Pythagorean theorem, square root 25 minus x squared. Now I've got my three sides. It's not changing anything. Okay there?